Welcome to the deep dive. We know you want to cut through the noise and get right to the heart of things without wading through piles of reports.
Exactly. Time is valuable.
So today, we're tackling a really big one. How we build and power our world more sustainably. We've gathered some key reports, and our mission really is to pull out the must-know facts and maybe some surprising insights about smarter building and energy.
It's a critical area. Let's dive in.
Okay, so starting big picture, buildings. Their impact globally is, well, it's huge, isn't it?
Oh, absolutely massive. The data, looking back at roughly 2010 to 2021, shows buildings using an enormous slice of the world's energy.
In the emissions side.
Just as significant. In 2021, buildings were responsible for a major chunk of global CO2 emissions. We're talking levels comparable to, a whole major industrialized country's annual output.
Wow, that really puts it in perspective. It's not just turning lights off then.
Not even close. And then there's the waste. Think about construction, renovations, demolition.
Yeah, the reports mention staggering figures.
Right. Globally, something like 100 billion tons of waste generated from these activities. And the really shocking part, about 35% of that just goes straight to landfill.
35%. That's a mountain of discarded material.
It is. And looking forward, especially in those fast-growing, developing economies, the picture gets, well, potentially worse.
I hope so.
Projections suggest that greenhouse gas emissions just from making the construction materials, concrete, steel, glass, could double by 2060 in those regions.
Double? From what baseline?
We're talking an increase potentially up to something like 3.5 to 4.6 gigatons of CO2 equivalent per year just from materials in those economies. It really flags a major challenge. How do we develop without ramping up emissions?
Which brings us to the carbon footprint.
Yeah.
It's more complex than just the energy used day to day, right?
Exactly. You're touching on embodied carbon. It's easy to focus on the operational side, heating, cooling, lighting. That's important, of course.
Yeah, the energy bills.
But embodied carbon is the hidden story. It covers all the greenhouse gases released across the entire life of a building.
Okay, so break that down. What does entire life mean here?
It means everything. From digging the raw materials out of the ground, shipping them, manufacturing them into products like beams or insulation.
Or an actual building process.
The construction itself, yes. Then maintenance, any renovations over the years, and finally, demolition and what happens to the materials at the end. Every single step has an associated emission.
Right, a cradle-to-grave footprint, essentially.
Precisely. And we measure this using a metric called global warming potential, or GWP. It's usually expressed in kilograms of CO2 equivalent kJ or euro, giving us a standard way to compare different impacts.
So it's specifically about greenhouse gases, the warming impact.
Yes.
How does that differ from embodied energy? I've heard that term too.
It's a good question. They're related but distinct. Embodied energy focuses just on the total energy used in all those stages, extraction, manufacturing, etc., regardless of the energy source. Embodied carbon specifically tracks the greenhouse gas emissions resulting from that energy use and the processes themselves. So using coal power to make steel has high embodied energy and high embodied carbon. Using hydropower would lower the carbon even if the energy amount was similar.
Okay, got it. Important difference. Now, where does most of this embodied carbon actually get released in a building's life?
Well, for a typical building, like a medium-sized office, the data's pretty clear. The vast majority happens right at the start.
Really? Upfront?
Yes, mainly during the product stage, making the materials, and the construction stage, actually putting the building together. That initial phase is incredibly carbon intensive.
Which highlights just how crucial material choices are from day one.
Absolutely critical. The concrete, the steel, the insulation, they all come with a significant upfront carbon tag.
And there was a compelling example in the source materials about swapping out common materials. Concrete versus bio-based.
Yes, that really illustrates the point. Take exterior walls, for instance. If you compare a standard concrete-based wall system with alternatives like sustainably sourced timber or bamboo,
What's the impact?
especially in warmer, say, tropical climates, the switch can dramatically reduce that upfront embodied carbon. Why? Because materials like timber and bamboo generally require much less energy to process compared to concrete or steel.
Makes sense.
But it doesn't stop there. Those bio-based materials can also affect the building's operational energy use. They often have different thermal properties, potentially reducing the need for active cooling later on.
So lower embodied carbon and potentially lower operational carbon. A double win.
It can be, yes. It shows how these choices ripple through the building's entire environmental performance.
Definitely makes you think beyond just the initial cost. Okay, so we know buildings have a big footprint. Embodied carbon is key. What about practical design strategies? How can we build smarter?
This leads us squarely into passive design, passive heating and cooling techniques.
Passive, meaning using the building and nature itself, not just machines.
Exactly. The goal is to maintain comfort, keep it warm in winter, cool in summer, by leveraging the building's design, its materials, and the local climate, minimizing the need for active HVAC systems.
Okay, how does that work for heating? What are the main techniques?
One fundamental approach is direct gain. It's beautifully simple, really. You design windows, usually south-facing in the northern hemisphere, to let sunlight directly into the space.
And that sunlight heats things up.
Yes, specifically materials with high thermal mass. Think concrete floors, brick walls, stone features, even containers of water. These dense materials soak up the solar heat during the day.
Like a sponge.
Exactly, like a thermal sponge. And then they slowly release that heat back into the room during the evening and night as the temperature drops. Free solar heating, essentially.
Clever. What about indirect gain?
Indirect gain puts a barrier between the sun and the living space. You have a thermal storage wall again, something dense and heat-absorbing position right behind the window glazing.
So the sun hits the wall first.
Right. The wall absorbs the solar energy, heats up, and then gradually conducts that heat through to the inside space over several hours. It gives a more delayed, steady heat release compared to direct gain.
That's okay, a slower burn.
Yeah.
Now, the reports mentioned a specific type, the Trombe wall. How does that fit in?
Yes, the Trombe wall. It's a very specific engineered type of indirect gain system. Picture a thick masonry wall, maybe 20 to 40 centimeters, painted a dark, heat-absorbing color on the outside.
Okay.
And then just in front of that dark surface, there's a layer of glass, single or double glazing, with a small airspace between the glass and the wall, usually just a few centimeters wide, say 2 to 15 centimeters.
So it traps the heat.
Precisely. Sunlight passes through the glass, hits the dark wall, gets absorbed efficiently. The glass acts like a mini greenhouse, preventing that heat from just radiating away.
Huh.
The heat builds up in the wall's mass.
And then slowly moves inwards.
Exactly. It conducts through the masonry. For a thicker wall, maybe 40 centimeters, it can take a good 8 to 10 hours for the heat to reach the inner surface. So you get warmth radiating into the room long after the sun has gone down.
That time lag seems really useful for evening warmth.
Mm-hmm.
What about vented Trombe walls?
Good point. You can add vents at the top and bottom of the wall, connecting the airspace to the room. On a sunny day, the air in that gap gets really hot, rises, and flows into the room through the top vents.
Creating airflow.
Yes, a natural convection loop. It pulls cooler room air in through the bottom vents, heats it, and sends it back into the room. It adds convective heating to the radiant heat from the wall.
But you need to manage those vents.
Critically important. You must close them at night. Otherwise, the process reverses warm room air, flows out the top, gets chilled in the airspace, and flows back in the bottom. It actually cools the room down. Needs a bit of user attention.
Makes sense. Okay, what about solar chimneys? Another passive technique.
Yes. Think of it like a specialized Trombe wall, often built vertically and maybe integrated into the roof. It's designed to absorb maximum solar radiation, heating the air inside the chimney structure.
And hot air rises.
Exactly. As the air heats, it becomes less dense and rises strongly, creating an upward draft. This pulls air through the building, so you can use it to draw cooler air in from shaded areas or lower vents, effectively driving natural ventilation and passive cooling.
Very clever, using the sun to power ventilation, and then sun spaces, or solaria.
Right. Sun spaces are like attached greenhouses, usually on the south side of a building. They combine direct gain the sun heating the air and surfaces inside the sun space with thermal storage.
How does the storage part work?
Often, the wall separating the sun space from the main house is a thick thermal mass wall. The sun space gets hot, some heat might transfer directly through openings, but the mass wall also absorbs a lot of that heat.
And releases it later.
Yes, it releases it slowly into the main living space, especially at night, buffering the temperature. There are variations, based on how the sun space connects to the house, different types of walls or openings giving different thermal effects.
Seems like a whole toolkit of passive heating options. The case study mentioned the Elda Day Trainees Hostel in Leh. That sounds like putting this into practice in a tough climate.
Absolutely. Leh is high altitude, very cold, but also very sunny, over 320 sunny days a year, apparently.
Wow.
The architect, Sanjay Prakash, really integrated these passive solar principles effectively. It's a great example showing that these aren't just fair weather ideas. They can work incredibly well, even in cold, sunny climates, to keep buildings comfortable with minimal fossil fuel heating.
That's a key point. It's not just for mild places. Okay, so that covers heating quite well. What about keeping cool passively?
One really interesting technique is the earth-air tunnel, sometimes called a ground-coupled heat exchanger.
Earth-air tunnel, using the
Yeah.
ground.
Yes. The basic idea is that a few meters underground, the Earth's temperature stays relatively constant year-round, much cooler than the air in summer and warmer than the air in winter.
Okay.
So you run pipes underground and draw the building's ventilation air through them. In summer, if the outside air is, say, 35 degrees C, passing it through these pipes cools it down significantly, using the Earth's coolness before it enters the building.
Yet in winter.
The opposite happens. If the outside air is very cold, maybe 6 degrees C, the relatively warmer Earth preheats the air as it passes through the pipes, maybe up to 16 degrees C or so, reducing the heating load.
That's ingenious, using the Earth as a free temperature regulator.
Yeah.
Okay, let's shift gears slightly. Water. The reports also painted a pretty stark picture of global water stress. How does this tie into sustainable building and energy?
It's deeply intertwined. Water stress, essentially, is when demand outstrips the available supply or water quality is too poor for its intended use.
And it's a widespread problem.
Very much so. The figures cited, even from 2010, showed between 2.2 and 3.2 billion people facing water stress for at least 1 month a year. Billion, with a B.
That's a huge number. Where is it most concentrated?
A lot of it, around 80%, was in Asia. Think Northeast China, India, Pakistan, specifically mentioned as hotspots.
And the future projections.
Concerning, especially for cities. The number of urban dwellers facing water scarcity could jump from around 933 million in 2016 to potentially 1.7 to 2.4 billion by 2050.
Wow. Almost doubling or more.
Yes, and India is flagged as likely being most severely affected by that increase.
And it's not just about quantity, but quality too, right? Pollution is a major factor.
Huge factor. Wastewater, which includes everything from sewage to agricultural runoff full of pesticides and fertilizers, is cited as the primary cause of water pollution globally.
And how much of it gets treated?
That's the shocking part. Estimates suggest over 80% of the world's wastewater just flows directly into rivers, lakes, and oceans untreated.
80% untreated. It's hard to comprehend the impact.
It has massive consequences for ecosystems and human health, and industry plays a big role here too.
In water use and pollution.
Both. It's estimated that corporate supply chains account for maybe 2/3 of global water consumption.
2/3. Which sectors are the biggest users?
Key sectors highlighted were food, textiles, energy, general industry, chemicals, pharmaceuticals, and mining. Together, they impact something like over 70% of global freshwater use and pollution.
So corporate responsibility is massive here.
Absolutely. And the overall picture suggests we're falling behind on goals. To meet the global targets for safe water, sanitation, and hygiene, the wash-you-wash goals by 2030, we apparently need to speed up progress by about 4 times the current rate.
4 times faster. Okay, so sustainable design really needs to factor in water efficiency and responsible sourcing right alongside energy.
Definitely. They can't be separated. Which brings us back to energy itself. We've talked about reducing demand through passive design, but what about the energy we do need? Let's talk alternatives.
Right. Renewable versus alternative energy. Can you clarify those terms quickly?
Sure. Renewable energy comes from sources that replenish naturally and quickly, faster than we use them. Sunlight, wind, rain, tides, geothermal heat, they're constantly available.
And non-renewable.
That's mainly fossil fuels. Coal, oil, natural gas. They formed over millions of years, and we're using them up far faster than they can be replaced. Plus, burning them releases greenhouse gases, driving climate change.
Okay, so where does alternative fit?
Alternative energy is broader. It basically means anything other than traditional fossil fuels. So it includes all the renewables we just mentioned, but it also includes nuclear energy and sometimes hydrogen fuel cells, depending on how the hydrogen is made.
Got it. Alternative is the umbrella. Renewable is a key part of it. Let's run through the main alternative renewable sources mentioned. Solar.
Solar's huge, obviously, incredibly abundant. We can harness it for heating water or buildings for cooling, for lighting via daylighting or electricity for lighting, and of course generating electricity directly with PV panels. You can even use concentrated solar power to create fuels. And it works even when it's cloudy, just less effectively.
Right, wind.
Wind power uses turbines, those big propellers you see, to capture the kinetic energy of moving air and convert it into electricity. It can be onshore farms or increasingly offshore where winds are often stronger.
Geothermal. Using the Earth's heat.
Exactly, tapping into the thermal energy from the Earth's interior. You drill wells to access hot water or steam, which can then drive turbines for electricity or be used more directly for heating and cooling.
Hydropower. We see lots of dams.
Hydropower harnesses the energy of moving water, usually water flowing from a higher elevation to a lower one. Dams create reservoirs, controlling the flow through turbines.
And reservoirs have other uses, too.
Oh, yes. Often multi-purpose. Drinking water supply, irrigation for farms, flood control, navigation, recreation, and energy. Hydropower is actually the largest single source of renewable electricity globally right now.
Interesting. Nuclear energy. You mentioned it under alternative.
Yes. Nuclear power comes from splitting atoms, fission, releasing enormous amounts of energy to generate electricity. It doesn't produce greenhouse gases during operation, which is a plus, though waste disposal is a challenge. India has several plants like Kudankulam, Tarapur, Kakrapar.
Okay. Ocean energy. Sounds promising, but
Mm-hmm.
maybe less developed.
That's right, still mostly in early stages, trying to capture the energy in waves, tides, ocean currents, or even temperature differences in the water to generate power. Lots of potential, but technically challenging.
And finally, bioenergy.
Bioenergy comes from organic matter biomass. That could be wood, charcoal, dung, specially grown energy crops, agricultural waste. You can burn it for heat or convert it into biofuels like ethanol or biogas to generate electricity.
Is burning biomass carbon neutral?
It's complex. It does release CO2, but the idea is that the plants absorbed that CO2 from the atmosphere as they grew. So if it's done sustainably, replanting what you harvest, using waste materials, the net emissions can be much lower than burning fossil fuels. But land use and sustainability are key concerns.
A lot of options then. And India's role in this transition.
Quite significant, according to the reports. India is now the world's third largest producer of renewable energy overall.
Third largest. That's impressive.
Yeah, and around 40% of their total installed electricity capacity is now from non-fossil fuel sources, which includes renewables and nuclear. There are also tools becoming available, like a solar rooftop calculator, encouraging individual adoption, too.
That's definitely a positive trend. Okay, so wrapping this up, it really feels like all these threads, building design, material choices, water, energy sources, they're all tightly woven together, aren't they?
Absolutely. You can't really tackle sustainability effectively by looking at them in isolation. Smarter building design reduces energy needs, which impacts energy source choices. Material choices affect embodied carbon and potentially operational energy. Water use is linked to energy production and building operations. It's all connected.
And making informed choices across the board seems crucial for making real progress towards, well, a more sustainable way of living on the planet.
It really is. The potential for positive impact is huge if we approach it holistically.
A complex challenge, certainly, but also filled with opportunities. Which leaves us with maybe one final thought for our listeners to chew on. Considering everything we've discussed, especially that upfront carbon cost of some sustainable materials versus their long-term benefits, what trade-offs do we really need to grapple with? What's most critical to prioritize if we want a future that's genuinely sustainable? Something to think about.